Hello, everyone. My name is Nathan, otherwise known as Old Man Builds, and we have Sean Calderon here today, and we also have the Benny Factor. Guys, how you doing?
Doing great. How are you?
I'm good, Nathan.
Doing really good. Jarvis let us know that he was sick. He's not able to speak. He may be in the chat, but his voice wasn't up to it tonight. Hello?
So I guess that's my cue then, huh? To start presenting.
Yeah, you're up, man. You got Electrets, but we do have a video later on from Jarvis, so he will be showing it. So I'll play that as soon as you're done with your presentation.
All right. Well, sounds good. Let me see if I can get my screen here shared.
There we go. I'll take us out.
All right. Let me know when you can see that gaudy lamp.
Yep, we can see it.
Awesome. All right. Hey, welcome everybody. It's great to share what's going on in my lab. And I first just want to say that I appreciate all you guys. I appreciate the love, all the kind comments, and I really like the questions. So I'm looking forward to sharing with you what's going on in my lab. So what you're seeing here is a thrift store lamp that I picked up for a couple dollars. If you look at the yellow sticker here, it still says Goodwill. Well, that's stuck onto this coil here. From my examination, it looks like it's what's called lead glass or crystal glass. So I thought, well, there's some potential in this. So let me see if I can take it out and what can I do with it? The thing weighs about 3 to 4 pounds, and it's not like regular glass. Lead glass is basically 24% lead oxide mixed with the silica, and so it makes for a shiny, clearer glass. This slide's out of order. This is the 33 gauge wire that I'll be winding on to that cylinder. And basically I'm going to be using it as the secondary of a Tesla coil. I picked up this cool winder. It seems to be like a version 2 of the manual winders that Amazon's been selling. The cool thing about this is you can just pick different size rods and place them in there, and it allows you to make coils quicker. You can keep the count accurate as well as save time. So I found this, and these bars here that you're seeing, when I go to thrift stores, I'll pick up the old junky laser printers or the old inkjet printers. And if you take them apart, you'll get a bunch of these bars. They'll be made out of stainless steel. They'll be soft iron, aluminum. And so this assortment of metals and lengths and diameters allows you, of course, to be used for this purpose, but I use them for other things. And so we'll see here in a little bit. Here I'm now winding that crystal cylinder, and this is tedious work. I enjoy it, but I'm not very good at it. This wire is slipping around and I have a lot of mistakes, but it's working. Here's another picture of it as I'm making progress. So every group of turns of wire, I'll squirt a little super glue. And then what happens is it gets all over my hands, and then the fumes sting my eyes. And then I say, hey, why am I not wearing the proper protection, gloves and eye goggles? And then I go back winding again, and then I repeat. I don't know what it is. I'm just pretty dense. But here it is. I'm making progress. The cylinder is about 13 inches long. Here's more progress. And here we see it's complete. It's rough looking, but it's good enough. Another picture of it. So here, what I did is I sprayed, you can get it at Walmart. It's called Rust-Oleum Clear Gloss. And I'll put a couple coats on it. I usually spray everything. I did make the mistake of saying that I sprayed my spheres, which I don't spray my spheres because it doesn't really seep into the grooves very well. But it works really well because it'll take any type of magnet wire that doesn't have a really good enamel coating on it, and it'll strengthen up that insulation value. So that way, when you use it as a Tesla coil, you don't get any internal arcing or any mistakes when you're sparking. Arcing and sparking. Now you can see it here. I'm going to test it with both a cylinder secondary and a concave secondary. Oops, I can speak. And I'm using the SciTube Archangel ZVS board. And so this is one of the first tests that I'm running from it. Now, it's pretty spectacular to get this on my first try. I know if you've ever built a Tesla coil long and skinny like this, and it's not easy to get it to project plasma like this. But yeah, it's the trusty ZVS, and this crystal coil just has some unique plasma discharges.
Sean, you see that ring in there?
Yeah, isn't that incredible?
Yeah, I was just gonna say, what the F? That is insane.
Yeah.
Is it the wire that's making the ring?
I think so. I mean, yeah, I can take another look at it. One of the ways to get these really small, narrow, tall coils to spark is to use that concave, that piping at the bottom, the copper pipe, is to get it shaped in the concave. If it's shaped in a cylinder like you see most Tesla coils, you won't be able to crank it up like this. I mean, I've got this little hair thick wire just putting out the amps. This is 6 amps probably out of this hair thin wire. So I turn on the 12 volts. It starts oscillating. Boom, you see it oscillate. And now then it's time to add the AC. So I'm going to work my way around here. I kind of wanted you guys to see different angles, and then I'm going to turn it on again and see what kind of shapes we can get. But again, I've never seen such a small, tall, thin secondary coil put out so much plasma like this. It's just incredible. And this ZVS board is different. It requires both a DC input and an AC input. But in the end, it makes life a little bit easier. You don't have to manage diodes and stuff like that. It's all built into the circuit. So pretty awesome little crystal coil. So I'm kind of trying to show you what it looks like on the inside, on the out. It's the video here doesn't show it, what's the word? It's not showing how really actually in person how pretty the thing is. All right, so now I'm going to place a stainless steel rod. I'm going to put it inside, and then we're going to fire off the Tesla coil and see what it does. So we have it already there, and let's see if we can see what it looks like. Now, this is not as exciting as I had hoped, but there is something interesting about this that I found that I'm going to do further testing. And there it is. So what happens is, if anybody's ever built a Tesla coil, this is what you don't want to happen, because the PVC pipe or whatever you're using as a pipe, it's going to start melting and smoking inside. But because this is like an inch thick of crystal glass, the fractals just dance all over on the inside of it, and there's no damage done to the coil. So this really excites me, because now I'm going to be able to stick all kinds of different metal objects in here and really juice the power. I'm sorry I couldn't do more with this in the little time that I had, but this is what I'm really interested in. I want to see how it affects the shape of the magnetic fields and the electric fields around it on the outside. I want to be able to see really what it can do if I can fill this whole center in with plasma, pure plasma. Because again, the beauty of it is that it doesn't damage the coil. So let's see here. So I'm going to take, okay, so after I did all of that, plasma inside the center. If this was a PVC pipe, you would see all kinds of scorching charcoal burn marks. The thing would be smoking, but there's just not even a scratch. It's like it didn't even happen. So that's why this has got me really interested, because I've not been able to perform tests like this with your average Tesla coil. And here's the stainless steel rod that came from an old printer. Oh, I'm also showing here no nicks or scratches on it. So very interesting. All right, so now we're going to get into the Electret. Now, I've read Jarvis's, patent application, and wow, is it so full of good information. And so when I read it, I sort of, in my mind, I saw the experiment that I wanted to do. So I 3D printed here on my Bamboo Labs printer a bunch of sphere forms. These are 1 inch in diameter. There's the bottom part of the sphere and the top part of the sphere. And what I'm wanting to do is fill those molds, those sphere molds up with epoxy, maybe some just hot glue from the glue gun, but basically things that are liquefied, but then harden over a period of time. And what I'm hoping to do, so here's some of what some of the materials that I'm working with. Here on the left is pure nylon. These are ball bearings. You can order them on Amazon. This is pure Teflon on the right. Left, it's pure nylon. And here are the forms that I'm speaking about. So I was thinking about different ways of heating up these materials, these spheres, to the point before they liquefy, and then zap them with high voltage DC. And the idea is to place all the electrons on one side and the protons on the other side, and then lock them in position. That way, then once the electric cools, it's going to have a permanent wave. Electric field. It's going to have electric field. So, a magnet has a magnetic field. So an electret has an electric field. That's about the best I can say it. And Jarvis is the expert. I'm just coming up to speed on these. So I took some resistors, I soldered them together, I placed them in epoxy, and this is going to be my high voltage DC probe. Because working with high voltage DC, you can either buy a very expensive probe, or you can build this and use your meters. And as long as you're using this as the probe, you're not going to have voltages destroy your oscope or your meters. Now, I did the calculations for these resistors. They're going to allow me to measure up to 30,000 volts DC. And so whenever I take a measurement using this probe, I'll have to times it by 50 to get the actual voltage. And it works for current too. So now I found some rusted old carbide steel ball bearings. I think they're carbide steel. They're indestructible. And so I thought, well, I'm going to need a consistent electric field, a high voltage electric field, in order to push the loose electrons to one side and the loose protons to the other side. And so I thought what I can do is grind little flat spots on these, and then solder wire onto them, high voltage wire, and then cover it in hot glue. Because if anybody's ever worked with high voltage, if there's any pointy parts, then you're going to have a discharge, you're going to leak plasma, you're going to have ozone. So what I did is I tried as smooth as possible to using my little cigar lighter here to heat up the sphere here, and then solder it to the high voltage wire. And again, with the idea of when the high voltage comes into the sphere, it's going to evenly distribute the charge. Therefore, it's going to put out a uniform electric field in order to then create the electret. I did, these are 1-inch spheres. These are 1¼ inch spheres. So I started out with seeing, okay, you know what? I'm going to put a sphere on each side, hook up the positive to one, the negative to the other, and then whatever electret I wanted to make, I was going to put in between them. Now, this all failed, but I'm failing forward. So here you can see now they're soldered. Now I'm going to put some hot glue on them. And if you look in the back here, you'll see here on the right where my arrow is, these are what are called high voltage generators. Now, they're not high voltage generators as they're listed in Amazon, but this small one here, you can put 3 to 6 volts in it, and it'll come out with, oh boy, thousands of volts. And then the larger one here on the right, you can buy those on Amazon. These are rated at the 6 to 12 volts high voltage generators. Now these output both a very high voltage DC as well as significant AC voltage. So these are strange creatures here. They're very inexpensive. So I thought, well, maybe instead of building my own high voltage DC power supply, I'll start with these and see what I can do. So the slides are out of order here. Sorry about that. This is when I take apart printers from the thrift store. I take all the poles, all the different materials, and I throw them in my drawers. So I always have them for multi-purposed. All right, we're back to the electrets. All right, so these are what the spheres look like. Again, the idea is to put something in between two of them, charge them up with thousands of volts, and then hopefully what's in the middle is affected in a way where it holds an electric field, like a magnet holds magnetic field. So now I'm testing these high voltage generators. I'm starting with 3 volts, and you can see it here. The plasma discharge is very different than what you'll see in a Tesla coil. And so you can actually see it here. I'm going to try to tune it in, and you'll see here that it actually looks very familiar. There we go. And you can see it. So that is basically the ring voltage of resonant frequency. The resonant frequency is 13.9 kilohertz, and this is the ring frequency. Now, this is important. These little high voltage generators, they put out both AC and a DC. The reason why the AC is there is it's because when it hits resonant frequency, there's a little tiny high voltage transformer inside, but before it discharges that high voltage AC, it has a little diode, and that little diode then rectifies the voltage, and so you get the high voltage DC. Now, one of the things that does not do this justice is that this white arc here, oh boy, let me move it back a bit. It's running away from me. Sorry, 1 second. I'm having too much fun. Okay. Come on, little guy. It doesn't want to do it. Let's try this. Here we go. Yeah, that's working. There we go. All right, so this plasma discharge is very bright. You'll notice that it's not that violet color or that purple color that you get from a Tesla coil. That light from a Tesla coil is not going to harm you. This white light here will harm you. If you expose yourself too long without eye protection, what I'm talking about is a light welding type goggles protection. This can give you a sunburn on your retina, and you don't want a sunburn on your retina. So this is loud. It sounds like firecrackers. It has a brightness that can harm your eyes. And if you Google it, it lets out a whole bunch of dangerous gases too. But other than that, it's really great to work with. Now, so what I'm testing here is that I'm going to see if I can put these two output high voltage wires. And then if you look up here, it's a little blurry. I'm going to then take my molds and my sear molds and inject them with some sort of liquid. Now, I don't get that far yet this week, guys, but I'm going to show you how far I've gotten. But next week, I will really have liquid, either two-part epoxy or hot glue, or I mean, if you read Jarvis's application, you can use on the other side of the spectrum, like ground glass. And so basically, electrets are in two different flavors. Either they're very positively charged, which are proton dominant, or they're negatively charged, which is electron dominant. So even though these are 6 to 12 volt high voltage generators, I don't like to run them over 3 volts. But here you'll see, oh, okay, I'm going to put 9 volts into it. And here, okay, so I want to stop on this. I'm using that high voltage probe that I showed you earlier. So what's happening is that this is a DC voltage. It's negative DC because I got the wires backwards, but it's okay. And since I'm using the probe, this is 169.9 volts DC times 50. I don't have a calculator, but if my memory serves me correct, it's about 8,000 volts. The difficult thing about using these little high voltage generators is they get really hot. And when they get hot, they start going out of tolerance. So instead of getting 21,000 volts out of it, which is with one of the generators that I tested, they can drop down to 2,000 volts and 1,000 volts. And they start to drop in voltage. And I'm thinking, what's going on inside? So I look on the infrared and you can see that they're just getting hotter and hotter and hotter. And what I learned, because I burned up a lot of these little generators, is that once you hit about 150 degrees Fahrenheit, it's toast. It's done. I don't know what it is. It's the diode that's melted, or the windings are melted. I don't know what it is, but this is the no-no temperature. So what I'm trying to do is keep these things cool, which they're potted in plastic, so it's not easy. And I don't run them for very long. I run them at low voltages, and my goal is to try to keep them under 1 amp of current. And my guess is that I can get about 10,000 volts and get some consistency. Let's say if I was going to put some two-part epoxy in, and I can run it for about 45 minutes. I'm really thinking I can get that far, and then that would be a point where the two-part epoxy would be almost in a solidified state. So here again, I have 3 volts. I put together this button. Now, this is worth noting too, and Nathan can definitely speak to this. When you're dealing with high voltage DC, Nathan works with the flyback. I'm here working with these high voltage generators you find on Amazon, is that the whole workbench will get electrified. And there's 100 different ways from Tuesday that you can get shocked. So I rigged this little switch here. And what it does is it works in conjunction with, so the steps are turn on the power supply. Everything's well insulated. I got on a rubber mat. I'm standing on a rubber mat. This is my ungloved hand, but I have a gloved hand. And this is how I add power to these powerful little guys without getting whacked or zapped. Let's see. There's the generator. So now, so what you're seeing here is I took 2 heat sinks and I drilled through them and placed these stainless steel rods, pulled out of printers and CD players, and that way, then when I'm getting a lot of arcing and sparking, which is very hot, the heat is dissipated off of these heat sinks. If you look to the left here, I have my molds. I'm ready to put my molds in between these two two wires here, and then try and get to build my first electret. Now you'll notice that I'm using this spark gap sort of device here instead of the spheres that I soldered earlier. Well, I felt like I was sort of overthinking it. So what I thought was, let me just get high voltage DC to run between 2 points and then see if I can get some kind of electret from this and then build up from there. I think those carbide steel ball bearings will still come in handy later, but I decided to come down to this approach. And you'll see a lot of recycled items here. I have the front face of some old stereo receiver. These are old stereo receiver heat sinks that I cut in pieces. So, and then the printers are the bars. So there's a lot of treasure in the thrift store. That's helpful. Save cost. I want to go back to this real quick. I thank you guys for your patience. I really appreciate your guys' input, that you guys are listening. It means a lot. Okay, so I don't think anything else is new here other than to show you that I'm working at 3 volts. I don't go higher than 3 volts. And my largest output has been 21,000 volts. This is in the not good range. I need it to be less than an amp. Otherwise, I'll be melting the internals again. So this is sort of a balancing act between keeping it 3 volts under 1 amp and then therefore setting up the environment to build the electret. This is optimal right here, 0.72 amps, 3 volts. That's great. That's what I want. And now I've opened up the gap. Now, one thing to mention here too is that you hear a sound and it's a high-pitched squeal. Also, you'll hear crackling. I don't know how to explain the crackling sound, but this whole area is getting electrified and you feel it. Now, there's no spark gap here. So what's happening is that this side is really trying with 21,000 volts of electrons to connect to this side, 21,000 volts of protons. This difference in potential is huge. Doesn't do it justice with these videos. And even with my camera can't capture the sound and the power of the room. Here's what it looks like. There's no quality control. Every little high voltage generator that I fry, I put the new one in, and look, it's similar because you have this ring frequency, you have the DC and the AC, but other than that, yeah, I think I like this waveform is because even though it only goes up a few gradient or divisions here, a positive, but it seems to drip really low below 0. So it's a really fascinating waveform. So here's a still frame of it. And this what caught me here as it goes up. Okay, from 0, 1, 2, 3.5. But here it goes 1, 2, 3, 4. And if you move it, it goes about 5.5. So it's really dipping way low and then high. And then of course it dissipates. Really interesting. Resonant ring frequency is what that's called. Let's see. Setting it up again, another high voltage DC test. Another ring frequency. And let's see here. Okay, so I'm testing the DC voltage. I fried another one here. It's 241 volts, so you'll have to times that by 50, which I think equals about, I forget, 12,000 volts. 12,050 volts. So 241 times 50. So I'm just really trying to lay the groundwork for my lab in order to be electret friendly, to build electrets. And so it's just all about understanding the DC and understanding the AC. Here we're going to see, this is what's really fascinating too, is that the AC is 500 volts. Okay. The DC you just saw was 12,000 volts. All right. So this will shock you in many different ways. it's and another thing that makes it a little scary is that we'll see here in a second here, the frequency, it's 14.7 ish kilohertz. So the skin effect is great up into the 150, 200 kilohertz and higher. But when you're this low, I mean, it's still having a little bit of skin effect, but it's going to hurt. I mean, it's going to hurt you. Well, if you don't know what you're doing, everything here is lethal. Don't do it. If you have some experience, you know what you're doing, you're still going to get a little fun zap. Okay, so I'm showing you a little bit better of how the setup's going to be. There we go. It's going to go in the middle there. I'm going to fill it with 2-part epoxy. I'm going to take off this because I'm not going to measure any of the readings. So I'm just sort of showing you my approach. I wanted to really pick Jarvis's mind, or pick his brain, I mean, to see what he thought of my setup and maybe tell me where it's not going to work well, or if it's going to work, or help me to add to it. So also you can see my little dollets over here for you Doctor Who fans. I'm looking to connect these to the high voltage and put out a very uniform, consistent electric field. And so they're in the waiting, but right now I'm going to start simple. There's another view of it. Again, so the idea is I fill this up, I zap it, I take it out, and there we have our electret, and it's awesome. As I was sharing earlier, glass is proton dominant, or it has a lot of holes and it needs electrons to stabilize it. And then down at the below here, Teflon, PTFE, is the most electron dominant, and it has an abundance of electrons that it wants to give over here to the glass. So all kinds of cool stuff here to work with, all kinds of stuff here to look into with different binders in order to create electrets. I'll talk about here in a second. Here's another series that I found interesting. Again, Teflon seems to win the prize as far as the most electrons in your electret. But here's some interesting ones, rabbit fur, hair, and so on. I don't like to deal with the living organic stuff, so I'll probably use mica. But I mean, you're free to do it if you want to build your own. All right, so that's everything with regarding the electrets and my progress. I just put that stuff together since the last presentation, and I was inspired by Jarvis. And so I decided to set up what was going on inside of my head. And now here's just a few miscellaneous things that I always like to share. Here I'm starting to wind a cone, and its dimensions are the golden ratio. And so I thought I'd share that. And so I'm using a white PLA filament in my printer. And this is, had I seen all of the junior high jokes that can come from this video here clip, I probably wouldn't have included it. But here I just printed these. These are 75% the size of the coils and the spheres that I've been working with, or I should say 75% the size of, let's say, the Death Star. And I'm going to be using these with the silver wire. See, I have different colors filaments, and the silver wire is very expensive. So I thought I need to really pick a nice color. I want it to be different. And so I picked this cobalt blue to wind with the silver. And the goal here is I'm going to wind the cobalt blue with the silver magnet wire 33 gauge. Then I'm going to wind these black 3D prints that are made from black PLA, but I'm going to wind these in 33 gauge copper. So black copper, blue silver. And so as I begin to run different experiments, I want to see how the silver acts versus the copper. And that will just begin the first test that I'll be doing with silver. I have a whole bunch of other stuff I want to do, but I thought I'd share. And these are my, basically my version 3. These are compact, powerful, easy to 3D print, easy to wind, easy to put in epoxy, and you can do lots of fun stuff with them. There's that beautiful spool of, oh boy, 2.5 kilos of pure silver 33 gauge wire. I think it's 4.5 miles. I forget the meters or kilometers. So one of the things I do is I really enjoy geometric shapes. So I have bins where when my 3D print fails, or I take things apart from the thrift store, and I just don't want to get rid of geometric shapes. So I have this little plumbing pipe. This cone came out of a vacuum cleaner. This is for, if you remember at the libraries, this is an index card holder. This is also another part inside a vacuum cleaner. And so I love just pulling from here when I need something. And it has to have some kind of artistic quality to it. And so I have all these bins. I'll probably share with you guys what I have. My wife and I, we attached to our house is an airplane hangar. And so I keep a lot of my stuff there too. All right. Oh, okay. So here, these are power supplies that I use. If you want to pay about $1,000 to $1,500 for a high current, clean DC power supply, that was hard to say. It's going to run you $1,000, $1,500, even $3,000. If you buy this kit, it's written here. If you buy these kits, this 24 means it's 24 amps, and it'll go up to about 67 volts, 68 volts. This kit, you can build it, and it's under $300. Now I know under $300 is still pricey, but if you really want clean DC, if you really want high amps, these are the power supplies to go with. And so I thought I'd share them. These are the kinds of things. Now, when I say kits, no soldering, okay? It's sort of like putting together a computer for a friend, and you pick this RAM and you pick this hard drive. It's similar to these. It's about 6 different parts. You order it, you piece it together. They're a bit deep. That's just because they put out a lot of amps and you need a lot of cooling. But these are great power supplies. I thought I'd mention them, and you get a lot. Now, this is an interesting sidetrack here, but I was going into my drawer of heat sinks. So if you take apart a lot of old stereo receivers from the thrift stores, you're going to get all these cool looking heat sinks, mostly aluminum, sometimes copper if you're lucky. I took 2 heat sinks. I probably mentioned this in another presentation. I was going to use them as a capacitor. So I sprayed them with the clear gloss so that way they wouldn't conduct. So I sprayed them in the clear gloss. So you see me pushing them together here in the bottom. Even though they look like bare aluminum, they're not. I sprayed them with that coating, enamel coating. It's clear. And now as I put them together, the air in between is the dielectric. And then, of course, the aluminum on each side are the plates. Now, what's super cool about this is if you look at my LCR meter, I have about 0.5 nanofarad. I'm going to zoom in here now. As I begin to squeeze those together, it goes up to about 7 nanofarads. 7 nanofarads, that's a lot. To have a 500 picofarad to about 7 nanofarads, that's a better variable capacitor than you can find. I mean, unless you can find one, I can't find them. And so I thought this was really cool. I thought I'd share it. If you have heat sinks, spray them here. Now I'm going to use it as a capacitor here to show you that, hey, this is not just on my LCR meter. This is actually working as a capacitor. So you can get the idea here. This is the stuff that I sprayed them with. Oh, okay. So one of the cool things about having the clear crystal secondary for your Tesla coil, you just get to do things that, like, I'm trying to figure out the strength of when the field, as it moves up to the top, it gets stronger and stronger. So down here, there's nothing. And you'll start to see that, okay, I get a little bit more plasma, but you're seeing it build up. So it starts off right about here. And that's interesting to me because this would smoke a PVC coil. That crystal glass is cooling things. And like putting metal inside of it and pumping it with power, you can also really have a fun time on the outside. That capacitor that I made out of the aluminum, one of the plasma discharges that I showed you earlier, the one that looked really cool, that was using the aluminum plate capacitor. So I thought I'd share that. And I think this is the end. Yes, this is the end of my presentation. I thank you guys for putting up with me for 44 minutes, as always. And I'll give it back over to you, Nathan.
Hey, Sean, can you put up that when you first did the Tesla coil on this one again, where we're doing that circle? It's
Yes,
like at the
let me find
beginning.
it. Yes, let me find it. I'm sorry, I'm all over the place.
Yeah, by the way, it was a great job.
Yeah,
Awesome.
Thank you.
amazing. Thank you, Sean. Love
I
your
appreciate
presentation.
that. Thank you, guys. I seem to have lost my feed, so I'm going to just jump out and jump in again. Sorry.
Okay.
Can you guys see my screen?
We can see it's on the same screen. Hold on. I got two of you now. Give me a
Oh,
second.
no. Okay. All right. How's that?
There we go. I can still hear you.
Awesome. And no echo. Okay. I'll find that video of the circle of the shapes here. Appreciate all the love, guys. Awesome. And it'd be great to go through your questions here in a moment here. I just want to find that video for Nathan.
You want me to pull this one off for you, Sean? This video, so you can pull the new one up?
I'm sorry?
You said you had a video to show?
I'm just going to go back on my presentation here to one of the clips.
Oh, you have it right there in the same. Okay. Yeah, because
Yeah, I
sometimes
have
you
it in
have to bring it down and put it back up with this StreamYard.
Oh, no. I can do it. Thank you so much.
Mhm.
I just need to find it. Here we go. Can you guys still see my screen?
Yeah, we can see it. It's still
Yeah.
doing the same thing. Can you click the back button on it? Will it work?
No, I'm sorry.
Oh, it's because it's probably a video. It messes things up.
Oh,
Yeah,
that's
that's what I
right.
was saying. Sometimes you have to bring it
Exit
down and
out.
put it back.
Yeah.
Yeah.
Yep. I'm going to go to a photo. Here we go. And then I can go to the video. Can you guys see that okay?
Yeah, we're still seeing the same thing. You got to take this one out.
Oh, I see it. Oh, okay. me do that.
There you go. Hey, real quick, while Sean's looking that up, I just want to thank Joe, and I also want to thank Aurora. We have 2 new members.
Oh, nice. Thank you, guys. Your memberships mean a lot to our team. They really help us out, and we're on a roll here. We're gonna crack this algorithm soon.
Awesome.
I just want to say on a personal note, thank you guys. I really do appreciate it, and I'm working to put a lot of member content out there that you should enjoy.
Yeah, no, you definitely have put out a lot so far. Definitely with the Star Wars, it's that had me rolling. Oh
Little
my
Star
God.
Trek stuff, little fun stuff. I also put some informative stuff, and I'll put some more stuff in there. Just so you guys know, the little emojis and stuff that I use in the chat all come from that Star Trek thing. You see them there on the bottom. We have different ones. There's me, there's Gerald, there's Ben, there's some shrooms in there. There's also we got a coil, we got a fire Joe in there. Looks really awesome. So I think we're getting close to adding another one too. So, but anyway, that was it. I just want to say thank you, and if you want to play with those during the chat and stuff like that, just join, and you'll be able to get all of them. Sean, did you find the video?
I think so. I have to start with this
Oh, there we
photo
go.
here, and then I'll go right into the video.
Okay.
I mean, that's the plan here. Sorry, let me just double check. Yes. It's forward. Okay.
Look at those fat diodes. Ooh.
Fat diodes.
I
Wait a
like the
minute.
fat diode.
I'm sorry. Okay, I'll ask it after this. Sorry. Okay, let's go to that video. Can you see my screen?
Yes.
All right. Let's see here. Here we go.
Oh, all right. Here's the video. Just trying to see if the wire's coming at an angle, and that's what's doing it.
You can see it bursting out the side too, which is because it's so active on top. And you know, Nathan, you've built a bunch of these skinny, small megahertz Tesla coils, but they don't really put this much output. At least I haven't seen it.
Oh no. And look at it's mesmerizing. It's
It is.
forming the ring and putting out all that extra. Wow.
There you go, Sean. You got to put that up as a short on your channel.
Definitely.
Sounds
You
good.
get lost in that.
I appreciate that, guys. I really do. I mean, I know it sounds kind of corny, but thank you, Juice is really good to run on sometimes. I appreciate it. So you just want to watch it one more time?
Yeah, that's wild.
This video should be like the feature for your channel when people land on the landing page. This should be what they see. This video right here. This is so cool.
I appreciate that. I honestly didn't notice it because I was just last minute, and you're right. It's pretty cool looking.
Yeah, everybody in the chat loves it.
Awesome. All right. Thank you. Let's see here. How can I do this here? Do
Plasma channel's gonna be jelly.
I don't look, honestly, I don't know my head from a hole in the ground with YouTube, so my channel's in a sorry state, but Nathan's gonna help me. So, and Ben too.
Oh no, you're gonna definitely grow, and you're gonna inspire other people who do stuff with Tesla coils, and it's gonna spread. It'll spread like wildfire.
I appreciate that. Thank you, guys. Thank you, Vortex, Ulysses, QUODTN. I have no idea how to say that. Thank you, Joe, William. Man, there's so many nice things in the comments. So, Nathan, you said you had a way of only filtering on the questions, or do you want me to skim through these?
Go ahead and skim through them. Yeah, because I started them last time, but we're kind of busy in the chat.
No worries. So the first question is Society of High Sciences. Think what burns your eyes is the high UV output. Yeah, I think you're right. I think it's a high UV that hurts your eyes when you're using the high voltage DC. Here we go. Here, William's saying he should wrap that with a magnet wire and seal it, and put that in the core and test what happens when the magnetic waves push against the electric. Any thoughts, Nathan, Ben?
It would be an interesting experiment to see if you can get that Tesla coil to get a heavy enough charge on it with a magnetic field, which I don't know if it's possible, in order to get an electric in the center of that crystal coil to put, you know what I mean?
Yeah.
Put a charge on it, but I don't know that that's possible.
Yeah, good point. Aurora was looking into a 1957 electrical engineering book this morning for electric materials and found a hole. Ben says, holy moly. Aurora says, section on cold cathode arc lamps and how they rig them up. There's a lot of cool stuff in those old electrical engineering books, or those old, not Scientific American, but the Popular Mechanics, Popular Electronics. A lot of cool project in those. See, Vortex says that his high voltage module did not work. I was in the middle of making it on the last video. I used a smaller one. So yeah, these, I don't know if you guys have ever ordered these off the internet, Nathan.
Yeah, I have. I have several of them.
When I first ordered them and played with them, I thought, oh my goodness, this is going to solve world hunger. I mean, I thought it was amazing. I had a nuclear reactor in my house, and then after getting shocked a bunch of times, and then they either failed a lot or they didn't work when they came out of the bag. And so it's sort of rolling the dice. I have a bin of about 30 of them. So I'm all set up for Electrets.
Wow.
But yeah, it makes sense. I guess the key is to really watch the current, keep the voltage as low as you can, and you'll get some time out of them. Thank you, Crypto. We love Sean's work.
I got a question for you. You show a spark gap above it. So what I thought you guys were just running positive to one and then negative to another, but not a spark gap.
Yeah, the spark gap's not desired. It's just in testing. You want to you want to see different distances to test the electric field. And so that's what I was doing. Yeah, sparks is what you don't want. You don't want that crackling sound. You don't want that high-pitched squeal. And so that's why you saw me soldering those spheres, because with the high voltage wire, the high voltage sphere, you're going to equally distribute the charge so well that you're not going to have those effects that you're losing electricity and the current's going to destroy that little transformer inside.
Okay.
And so that's where the extra care is. But the reason why I had the spark gap is to show how electricity DC is going to go at a high voltage through whatever is in the center. But I should have mentioned this earlier, without the sparks.
Okay, but again, let me just go over this because I'm kind of unsure about this. When I asked last time if you put one on each side, I was told no, that it would be one only. So if this is your positive and you had a tube and you had a bolt on the end of that tube, you just hook that anode to that bolt, and that would be your, say, positive charge on that one. Is that wrong?
So it's not wrong in what you're talking about. So I'm talking about, this word's used quite a bit, but the dipole, or we'll just say two poles. So when people say dipole, they usually refer to a magnet and it has a north and south. Di is two, pole is is either the top or the bottom. What you're referring to is what would be called a monopole.
Mm-hmm.
And so a monopole was literally just has the positive or just the negative. And so I think
Okay.
that's what you're speaking of. I'm going to be building a positive and negative electret or a dipole. Now, I have no idea what I'm talking about. So
So you
Jarvis
want
is the expert.
the ball to be negative on one side and positive on the other.
If I'm creating a dipole. Mhm.
Okay, that's what I'm asking. Okay, so it's
Yep,
different
yep.
than what we were talking about last time. All right.
Yep. One pole, monopole, that's what you're talking about. Only
Mhm.
one wire. And then everything charges the electret to just one field. Either it's a negative or a positive, that's it.
Okay.
I'm trying to do what I think is the easier is to just add the massive high voltage and then put something in the middle and hope for the best.
Okay.
So all right, well, some love from Crypto, thank you. Let's see, looking through, there's some off-topic fun in the chat as usual. So people are talking about the plasma channel. I think my channel having 50 subscribers is already scary enough. So I don't know. I'm happy with you guys. So I like our little community. Let's see here. Right. Aurora says, okay, wait, I don't even know if I should say this. Aurora says blue balls are the key to good steady stream in the middle. Oh no. Yikes. I don't even know why I wrote that. Sorry guys. I'm dense.
You might,
We've all done it. I've done it. Just the last podcast. Remember
That's
with the
so
chocolate
bad.
bubbles?
Holy cow, I'm sorry.
It's
I'm very
okay.
slow in the uptake.
you might
Oh,
want to
man.
read them first before you say them out loud. Especially in this chat.
I know I'm now reading them in myself and yeah. Sorry about that. This is a family-friendly channel, so
It's okay. Like I said, it just happened to me.
oh boy. So, horrifying. So Society of High Sciences makes a comment here. The spark gap will cause the current to take on an impulse wave. So there's some resonant frequency going on inside. And of course, that's where we get the resonant frequency waveform. And I think that's what's sort of emanating as maybe like a transmitter, whereas the DC is coming out as the final product after the diode. It's a tough one to explain. Spark plugs could work too. It's interesting. They could definitely handle the high voltage. A ball of ice. I've never thought about that. A ball of ice. That would be a really good way to become part of the high voltage circuit. But I'm not the. What's that?
Yeah, you say put it the high voltage to the ice?
To the ice ball.
Oh, if it's being frozen at the time you're putting the electricity into it, it'd be very interesting.
Yeah, exactly. Yeah.
But I wouldn't want to be touching it or be near it.
Yep, turn it on and run.
Yeah.
So we're getting comments on the Tesla hair pit circuit that we always write down and then forget about. So I'm going to write it down again. Sorry about that. Because it's always interesting, but yet we never move any ground on it.
Mm-hmm.
Let's see. I'm just going to write it down. Thank you, William. He loves what he's seeing. Let's see here. Anthony says, keep building stuff. It's a Frankenstein movie. Sorry. Yeah, I sometimes feel that way when a lot of voltage is flying. Thank
And
you.
also I was thinking, because you also source so many different parts, you have all these different parts lying around. You just like
Mhm.
whip something together with, like, yeah, Dr. Frankenstein. That's awesome.
Yeah, thank you. I really appreciate that.
What's up, Mike?
That means a lot.
Hey, Mike.
William says, "Hey, Mike." William asks or says, "What we are watching is real science." Oh, that's
That's
cool.
right.
Thank you. Plasma Channel recently made a video about electrets. I kind of wonder about the Plasma Channel. I had presented my Tesla coils that are immersed in two-part epoxy. And so I'm able to drive these really high voltages with very little input because of the two-part epoxy. And then the plasma channel comes out with this little transformer that's in two-part epoxy, and he creates large outputs of it. And then we mentioned electrets. We just started talking about it. Then on the plasma channel, he makes electrets. Now, I'm just saying these are coincidences, but if he starts looking like, he comes out with a crystal coil and he's putting stuff inside of it, we're going to know that he's yeah. So, but I did
We
see it
gotta
actually.
we might have a secret fan, is what you're saying.
And if it's that, yes, as long as he's not putting out any copyrights or anything, that's cool. He'd be cool to have a secret fan as a secret
No,
fan.
you know what? I actually built his ion thruster. It works pretty good. So
Wow.
yeah, it was really cool. He got a patent on it too. So he contacted me because
Nice.
I had a video that looked like his, and I guess his attorney just wanted to clear it up so that he got all of its credit. And yeah, he was actually really cool. And
Wow.
he said I did a good job. So it was awesome.
Awesome. Yeah, he looks like a great guy. He really does. So William mentions that it's static electricity, and that's correct. And this is where I think there's a lot of confusion. Static electricity is DC, but it's DC in a way where it's on an insulator. So you have all of this DC voltage on an insulator. Let's say it's on your pair of wool socks. You have your wool socks, you pull them out of the dryer and they make that crackling sound, and you can see all the little hairs on the socks, they're sticking out straight. That electricity cannot go anywhere because it's on an insulator. Now, if it was on copper, it has a conductor, it would actually flow. That's what we call electricity. But when it's stuck there, it's called static electricity. When you touch now that sock and then your foot touches some part of metal and you get zapped, then that's no longer static electricity because it's moving. That is direct current. Now it's super high voltage, super low current, but it's no longer static electricity. It's just DC. And I don't know if that helps because I was always confused. And so I looked it up, and it's been really helpful in my experiments to know the difference.
That is very helpful. Thank you. Because I've always been confused with that as well.
Yeah, it always felt like it was something completely different. And no, it's just electricity in a different form.
Mhm.
So the note here is the magnitude of the discharge increases the larger the gap. It gets louder as you pull the rods apart. That's very true. Super loud. It's a spectacle. I mean, I'm probably going to see if I get some close-ups. One of the things also about using that fierce discharge of high voltage DC, it affects all the equipment around it. It's like a little EMP device. It'll
Mhm.
have your phone shut down, or it'll start scrolling and then run an app. I have these lights where you just touch it and there's no button and it turns it on by just the touch. They all start turning on and flickering, and it's quite an effect. And in fact, if you connect these little high voltage generators to a coil, you will have an EMP device. You can disrupt cell phones, you can disrupt laptops, and they're very serious. But that's how simple it is just hook it up to a coil.
No, I was disrupting my computer just earlier today.
Oh my
Hey,
goodness.
every few seconds. doodle-loop, 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 doodle-loop.
Yeah.
Sometimes it'll change the channel for me.
Mhm.
So it'll scroll through YouTube for me as I'm hitting the high electricity in the garage.
That's
So
awesome.
yeah, it'll just keep going to different channels and playing different videos. I never know what's playing over there, man. I can't hardly hear it, but I can sure hear it changing the channel.
That's
You gave
awesome.
your computer Adderall.
Yeah. I don't even know what's on, man. I look over there and I see all kinds of weird stuff, and I'm going, oh no. My whole page is going to be filled up with this junk.
That is funny. Yeah.
That's funny.
You'd think the Tesla coil would be more damaging, but it's not.
Oh,
It's
not even at all.
it's okay. Don't get me wrong. A Tesla coil has its little effects, but the arcing of the high voltage DC is the most effect. Has the most effect.
Well, wait until you put the that field like on the outside of something, and then you rotate 2 discs with Tesla coil attached to both the discs. Man, it just shoots it across the room. So
Wow.
in an instant, you'll have things lighten up across the room, and you're like, "What's going on here today?" You know what I mean?
Yeah.
It's really a cool effect. We go
Some kinda-
outside.
Yeah,
You
some
can-
kind of DC origin story happening here.
Oh man, you go outside, you can just light it up, man. You can push that thing far, but you better take your cars out of the driveway if you know what I mean.
Yeah.
Oh, it'll fry them.
Yeah.
Yeah.
Oh wow.
It's that extreme. Yep. And you're generating such a high powerful electric field that it's inducing charge all around you, and everything around you are different types of insulators, so they're just holding the charge.
Yeah.
So yeah, it's incredible. So there's a comment here: Tesla used an impulse because it's closer to the dielectric or voltage, allowing for different material to more easily absorb the energy. I thought about this. Instead of having a constant direct field, so one side's always stays positive, the other stays negative, but it's a flat. There's no ringing, there's no anything. But I did think about, what if I just sent positive pulses at it and just sort of slammed it with positive pulses? Would it cause the electrons in the material to be more responsive, to get polarized? Or is it to have it in that steady field that keeps the atoms aligned, where it when it dries, the binder dries, holding everything together? Is it gonna react better?
Yeah, do you want to force it into place, or do you want to subtly, like, gradually? Is that what you're trying to say?
Right. Is it finesse or is it a machine gun? Now,
Mm.
I wouldn't use the word finesse with 12,000 volts DC, but I guess it's maybe analogous.
So I would imagine a steady field that holds it there, but you want it to be pulsed, because every time you pulse it, you're getting more to push towards that field. So the higher the amount that sits in there. So you would have to pulse it a little while before anything even goes in there, liquid, to bind it, wouldn't you?
Yeah, that's a really good point. So Jarvis's idea is that when you shake them up, He calls it the bake and shake
Hmm.
in his paper. So heating up would make sense. The shaking would be sort of a what is it, like a, oh my goodness, a punching or a pulsing, if you will. But that would just dislodge them. You would need a static field to then align them. Is that what you're saying?
Yeah. But
So
you need to charge them. So I don't think everything get charges at once. It's kind of like the difference between just running straight DC and then pulsing DC onto like your coil or something, and then you have a magnet flip, right? It's
right.
kind of the same effect. You don't want to just hit it with just straight DC. You want to pulse it.
So are you thinking mixing the two, or are you thinking doing one and then the other?
It's got to be in a liquid state long enough for that pulse to take effect in order to put that charge on them well enough.
That is key. Exactly. That is key. So William makes the point he can't wait to build his own lab. Awesome. Good luck on that. So these have been used as stun guns, according to Anthony. That is true. You can actually convert these into a stun gun. But because you have no idea what's inside of them and no idea what's going to come out of them, they could be very dangerous.
Mm-hmm.
Let's see here. Lots of love in the comments. Thank you, guys. So here it says, use Downy, also good mixed with water for anti-static spray. Yeah, the fabric softener actually has a lot of effect on some of the things I've been trying to do. One of the insidious things about fabric softener is when I take a cloth out of the towel bin and it's just been washed and dried, and I go and clean off the plate in my 3D printer, that plate is no longer sticky. So when I'm doing 3D prints, it can stick to nothing because of that fabric softener. Fabric softener can also remove the static effects that you want. And so, yeah, it's interesting how it comes into play. I learned that the hard way.
I'd never use that for that. I'd use rubbing alcohol.
So I was just wiping it clear with a little bit of wet, like a wet towel. But then after everything was slipping, I looked it up and it says, hey, do you use fabric softener? Do you use those towels to wipe off your build plate? Yes. One of the things that has been helping my build plate stick better is Windex. Have you heard of that, Nathan?
No, like I said, I just use the rubbing alcohol. Not rubbing alcohol, excuse me. Isopropylene or something. 90, yeah,
Isopropyl.
90 something percent.
Yeah, I've heard that too. It's a little bit harder on the plate. Windex, I think, is a little easier on the plate, but it sounds like both of them will work.
Oh, I use that stuff on everything, man. It dries real quick. It's instant, and it takes off the oils from your fingers really well. So
Yeah.
anything like if you charge the pipe or something like that,
Mm-hmm.
you'd want to clean it and that stuff so that it's perfectly clean, evaporates quickly, and there's no residue left behind.
Yeah, that makes sense. I use alcohol on everything. I just because then I know my surfaces are ready. Because you're right, a little hand oil, a little something, and that will affect your experiment later. William says insulators make good electrets. Yeah, that's true. I don't think you can have a metallic electric. I think there's too many free electrons. So society says interesting polymaterial have the highest negative factor. Yeah, the triboelectric series of materials is fascinating. Which has the most protons, which has the most electrons, and these are just items that you have in everyday life. Polygon says you can dope material as well. That's true. So mixing combining two kinds of proton dominant materials or two kinds of electron dominant materials. So yeah, doping sounds like a cool idea. Vortex says, I'm wanting to try sulfur powder as negative aggregate. So Vortex, who is Jarvis, is the electret expert. So we'll be referring to him. And now there's some talk here about different materials, and there's a lot of fun, some joking. Sorry, I'm being annoying.
Hey, Sean, we got a video from Jarvis.
Yeah. I think we're mostly through the comments here. You want to go to it?
Yeah. Let me. Now, I haven't watched this before, so hopefully everything's good, but it should be. Let me. There's no volume on it. Okay. Let's see what he's got here. Pharaoh's rod. Kind of, man, I wish there was a typed part to this. Probably just showing the stuff you need.
Oh, so the sound is just impossible.
Yeah, there's like no sound.
Wow.
Let's see his setup. Let's see what he's got going on there.
The way he's chaining those neon lights. Look at that. Neon bulbs.
That's cool.
They take about 90 volts each. So they're basically a high voltage, not an incandescent, but
let's go back to that a little bit. We'll just.
His setup is so cool. He's got the PWM right there, the pulse width modulator. Yeah, he knows what he's doing. That's crazy, though. Do you notice that the other end of those lights aren't connected to a wire? This is one wire power.
Yeah.
He's doing something. The electricity going between those two string of lights, if you go in the middle there's a lot of electric field going on in there.
By the way, you can't, with those high voltage modules, just so you know, you can't connect both sides like that.
Oh, try to hook them in parallel or series?
You're gonna blow that light completely up.
They eat each other up. I've tried it.
Yeah, you gotta have an open circuit.
Yep.
So let's see.
2 LEDs. 100K resistor. I still want this video. Yeah. You don't want your supercharged balls to explode or implode. See, I always fall into that. I just read it again. I'm so sorry. Oh my goodness.
Oh dear. Oh.
Wow, I didn't know that.
Yeah, we're gonna have to get some context to some of this on the when he's able to speak.
Yeah, I think you're right.
Yeah, there's a lot. It's a lot of information there, and it'd be better broken down if he was able to tell us what it was.
Yeah, I think so.
And hook us up with some of those shrooms.
Yeah, what I'll do is I'll go through it and I'll screenshot each one so I can zoom in on it later when we do the, when we do another presentation on it. That way it's easier for everybody to see.
Yeah, that sounds good.
Yes, he says it shows formulas in there. Yeah.
Mm-hmm.
There's a lot of information in there. I saw that.
Yeah, I can't wait to dig in. It looks so cool. I'm looking for Jarvis's comments.
They're at the bottom there.
I see. Yeah, he was the one I was hoping to check out my hokey setup and tell me how to fix it.
So right there, he's given a formula. I think that's what he wanted to see.
Oh, the equation for okay. So there is one thing interesting about the correlation between a capacitor and electret, because a capacitor can hold charge, an electret can hold charge, but a capacitor will discharge over time. It has leakage current. It has other forces inside where a capacitor will decrease in charge and then not hold a charge. Whereas an electret is supposed to be more like a permanent magnet. A permanent magnet will hold its charge, will lose its magnetism 10% every 100 years. And so an electret sort of fall into that similar class. It would hold its charge and only decline minimally over long periods of time. Now, in looking at this, I cannot wait to dig into this equation. He's using aluminum foil, plastic wrap, and I wish I could break these down real time, but it's cool stuff. Ian has a question. Did you try putting a wire on the steel rod down the center of your crystal Tesla coil and measure the OWE? Oh, that's a cool acronym. I wonder where that came from. The one wire energy. So there should be a little copyright there next to OWE because that's Nathan's. Nathan has introduced that to the scientific language. So pretty cool. I have not put a wire connected it to the rod, but it would be very cool to see if I can measure the energy. That sounds like a very interesting idea. William says the plasma ring seems like a xenon ball. Have you guys ever seen that ring inside that? What do they call it? The toroid. It's a white toroid floating inside a high voltage glass. I don't know what it is. A light. Have you ever seen that before?
Yes, I've seen it. It's like a torus shaped plasma.
Torus-shaped plasma, exactly, Ben.
Mm-hmm.
I think William is saying it's similar.
Yeah, you can see it like spinning around.
And you would expect some random spinning because the electrons are coming in randomly, leaving randomly. Why would the wire make the sphere, the torus?
Well,
isn't that interesting?
Yeah, but it didn't show the tornado underneath it. So usually there's a bunch of little ones that go along with it underneath it.
Oh.
And you were just getting the top one, which is even more amazing.
I didn't even notice it until you pointed it out. I'm just looking through the lens of the camera. But yeah, oh my goodness. It's a great discovery. All right. There's some more junior high bathroom humor. I
think we're at the point where comments are going to be out because there's going to be a lot of that.
Yeah.
Let me just pull up Ian's video because I wanted to show this as well. All right, because he has that capacitor, Sean, that's got all the multi stages. He says it's a Master Evo design.
It's. I so want to build this. It's the variable capacitor. You can adjust any capacitance.
I've been asked to show how to build these capacitor switching boards because they're particularly useful in getting resonance out of strange scenarios with test the coils with rods down them attached to rodent coils. So they're very useful for changing capacitance within the actual coils themselves when they're resonating. Yeah. Where did that happen? Shit. Weird. All right. Well, that's just an example of what happens. Sometimes it throws a bit of a wobbly. That's about 2.3 kilovolts there, and it's given a frequency is about 124.6 kilocycles. It kind of likes that 124, 125, but you can get it from so many different combinations of capacitive loading. It's very strange. And it'll disappear, and then you'll put some in and it'll come back, or then you'll take some out and it'll drop down, and then you take some more out and it goes shooting up. So it's very strange. Anyway, but it's useful to get it. I've got a discharge. This is just DC low power, 12 volts going in. So got a bit of a discharge there, but I'm just running another experiment at the same time. So anyway, so that's basically what they're used for. I've got two here in parallel, and obviously in parallel with the ZVS board. And so because I just ran out on this, and I had to put another one in to start be able to manipulate that as well. And that's what they're useful for. It's great. You've got 2,000 volt capacitors everywhere here, which is fine for parallel resonance. But if you're going serious with series resonance with this stuff, I've got 6 kilovolt versions of it. And rather than switches, you need little jumper cables to go in between the green terminal posts. But anyway, I'll show you how to basically make a board. Okay, so I've laid out. I've ordered a bunch more capacitors. I should have checked the pin distance, because the MKP 10s are basically like these, those are 22 nanofarads, whereas these are 2.2. So you can see the footprint is much larger if you get FKP ones instead. But I basically got what they had in stock and thought I would just crack on and get it done anyway. So yeah, I've got a couple of 47s, 22s, 10s here, then smaller down to singles, and then 100 picofarads down at the bottom here, just to try and cover everything. So there's 336 nanofarads total on this board. Basically, this perf board is there's no metal on it at all, and that's better for high voltages. Also, credit where it's due, this is actually a Master Evo design. He came up with this maybe about 4 years ago, and I saw it and thought, well, it's brilliant, perfect for what I needed, and I've been using them ever since. So thank you, Master Evo. So basically, I've laid them out, and I've put just marked out where I'm going to put these switches. They've got a reasonably small footprint, so I'm going to just put them in like that, and the switches protrude enough so you can actually get to them. It's a bit crowded in this board. There's going to be like 40 switches on it, but I've only got 30, so I've ordered another 10 just to have enough to get it all done. But anyway, so 6mm drill bit seems to make the right hole size for these switches. And yeah, these are single throw, double pole, something like that, STDP. And yeah, so I'll just crack on and I'll get the rest of the holes built, install all the switches, and then I'll take a look at how to wire it up at the back. Okay, thanks. All right, hello again. That's a rather dull task of putting all these switches in. I'm still waiting. I've got 10 switches missing here, but I've been cracking on anyway. Yeah, these stands are really useful for doing things like this. You can spin it over. The common traces, I've put those in. These are the, I mean, it's obviously it's not polarized, but if you put all the feet that are together away from the switches into a common line, then that will then work, because this one works across here and across the back here. So it covers all the switches and the switches to go in. Then you can feed the end result of that back to the terminal posts, which will be in the other side. I'm not putting those in until I get these switches in, and then I'll put them on the outside. But as you can see, I've just traced out the lines that made most sense for it. You've got all the single inputs here marked in red toward the switch that they're going to go to. And I want them all to switch on in the same direction. So some of these will come across to the actual activating pin here on the far side, whereas these are simpler because they're just going straight to the top because of where they are in orientation to the switch. But that's basically it. The common line that goes through the center of the switches is obviously for the other side of the capacitors, which is being switched. So they're being switched in and out in parallel. And this is the other side, which is just constantly on, going to the other input to the capacitor board. So again, we've got the one common to the pin that is parallel in all of the capacitors, and the other side of the capacitor is in parallel, but with a switch on it to switch it in and out of the circuit itself. So all of these need a separate little wire going to each of the single switch inputs, which are then switchable on and off to add them and take them out of the circuit. Okay, so I'll update when that's finished as well. Thanks. Okay, so I've got all the little white wires are the other leg, the remaining leg of each capacitor being connected through to the switch. And so I've got all the wires connected for all the switches that I have, still obviously missing those 10, but this is getting it into a usable state. So it'll be quick and easy once I get the other switches in. So I'm just going to test it out and make sure everything is going as it should. Just connect the...
Hey, real quick, guys, I just want to tell you before we continue with this, I'll show you an example of how this board works. He also has a diagram at the end.
Multimeter here to the two lines of the capacitor, so that everything is switched off, all the switches in the down. I wanted them oriented one direction. Stop confusing myself. And okay, so that's on. That's a 47. It's showing 44.5. There's another one, which is 44.5 again. And I've been through all of these, and everything works fine. All right, so yep, cool. If anybody needs a schematic, I could give one, but it's really straightforward. And you see the way the switches are connected here. I oriented all the switches the same way up. So I think the writing was on, looking at it like this, the writing on the switch body was on the right-hand side. So that always meant that putting it up is going to switch it on, and down is off. So that's how all the switches are configured. And to maintain that integrity, I just put a little red dot on the top, on the two parts of each switch that are active, so it didn't tempt me to go straight from here to that leg, and then that would reverse the switching. So just something to look out for. Any other tips in this? Yeah, I tend to, when just putting these wires together, is just cut them all first of all, and then just using the tweezers here, I'll actually bend the wire around like that. Oops. Ow. And then just hook it on, guide it round where I want with the other end off, make another circle on that, and then just wind it around the leg of the capacitor, tighten them up at top and bottom, and then go on to the next one. And then just solder them all as a one thing. So there we go. Yeah, again, just to reiterate, one leg of every capacitor is on a common line, so they're all connected essentially in parallel, but the other leg is switched in and out of that parallel circuit. Simple as that. It's really straightforward. Time consuming, but very useful. All right. I hope that helps, and thanks for taking the time to watch. Thanks very much.
So as you can see, he drew out the schematic for you.
Oh, there we go. Nice.
Yeah. So I made it relatively straightforward on what he's doing.
Yeah, see, this is a little bit clearer for me because I've worked with the 2-pin capacitors, but not the 3-pin before. So this actually clarifies a couple of questions I had.
Yeah, the work is the craftsmanship. He did a great job. It's amazing. This diagram is so helpful because when I looked at it first, I thought, oh my goodness, I was overwhelmed, but the complexity and but this is great. You always have a need to swap out capacitors, and they can be expensive. Build one of these, and you save yourself a lot of money.
Well, yeah, it makes it easy to find the frequency on a Tesla coil. That's for sure.
Yeah.
Yes.
So
Just dial it in.
Yeah, I wanted to show that too, because he has another video on his channel where he's just setting this thing up. Let me see which one it is.
Ooh, an Ian Encore.
Yeah, he's got his own channel, guys. Just click on there and subscribe and put it in the comments.
Awesome.
Did you put it, or you want me to put it in? I can put it in if you want.
Yeah. Oh, he's got the Sean stuff. Okay, hold on. He shows the board here. Just trying to see if it's the right video. No, I think it was a different one. So it might be this one. Yeah. Okay.
$20. That's a tuning bank for it. It's a tuning capacitor bank. It just really helps. You've got 100 picofarads here, 1 nanofarads here, 10s, and then bigger ones here, but that's for other stuff. And using Sean Caldwell's his adaptation of schematics is ZVS board, and that's a coil I had, and I just made the primary to do this test. 3D printed a top there, so I've got 4 rods that I can put in, but I'm just using one just for this test as it stands now. The rod has nothing connected to it at the bottom. I haven't looped it or anything like that. The bottom of the coil is grounded, and obviously just the ZVS is going into either side of the primary. The probe is there. It's about 10 millimeters off the edge of the secondary coil, and I'll switch it on and we'll see how it goes. Yeah, you need to have this switch here, because if you just turn on the supply, it just it doesn't trigger the circuit into oscillation properly, and it just pulls amps through everything and wrecks stuff. So the switch, it gives it that jolt. There it is. It's on, and yeah, 0.2 amps. So that's good. That's sensible. I usually get this blurry nonsense off the current probe initially, but what I will do is I will now start switching on each nanofarad. Okay, so that's 9 nanofarads there. Now, once it settles down like this, I can start to switch them off. It's totally bizarre. And it increases the frequency, obviously, but it also increases the amplitude of the, let's see, if I go one too far, it shuts down. Let's see, nope, it's still there. All right, nice, okay. Interestingly, so the current probe is on the 1 wire coming off the brass rod, and it is showing 180 degrees out of phase with what the probe is picking up from the actual coil itself, which is interesting. About 1.64 kilovolts there, and it's what's that? Oops, not to be touching the. Oh, okay, let's try that again. I hit the wire. So I just put in all the other stuff again.
That's so cool. He just does that.
It's totally weird the way this works, but anyway. I'll just show you. That's the one wire. I've got a couple of fluorescents here, and they get brighter and brighter as I reduce. I bring it down to literally 1 nanofarad. We're back to 1.64. The frequency is just under 700 kilocycles. It's about 695 or thereabouts. Moving around a little bit, but it's fine. And that's a 20 volts, 0.22 input. And as I said, there's just the 1 nanofarad is left on. Everything else is off. So I'll increase the voltage a bit here and just show you. So both the current response and the voltage response is going up, and we'll just lit up brightly there. That's me up to, I'm at 30 volts. I'm not going to push the ZVS board because, unlike Nathan, I hate frying stuff. But look at that. This is I've only seen this until I saw Nathan do it. I have only seen this maybe once or twice online ever. And it is just so awesome to see. That is just one wire. And that's the end of it. That's the end of the wire. You can touch it perfectly safe. Don't look.
Oh
I guess that's
my.
either my heat or my capacitance that is causing more draw through from that single wire.
Wow.
It's just incredible. A wonderful thing. Thank you, Nathan. Anyway, thanks for watching. Cheers.
So does he have to even have that second wire hanging off there? He can unhook that and it still work, right?
Which second wire? The little wire that he was touching?
Yeah.
No, he doesn't have to have that at all. It's just an extension. He can just clip it onto another light or whatever he wants.
Right, to string them together. Gotcha.
Yeah, because this one continuous stream, one to the next to the next. That's it.
That's so cool.
Yeah, he's got that thing going on. That cat bank is awesome, by the way. Like,
Yeah, I have to get myself one of those.
I've always wanted to try and tune my coils down to the picofarad, and I think Ian's board will allow that. It's always in the back of my mind that I'm down to nanofarads, but what would happen with the picofarad level? So that's pretty awesome.
yeah, he said he got the design from Master Evo, and you know how he is with his Tesla coils. He's a genius, so it's great, man.
Yeah, Master Evo is the master at a lot of things.
Yeah, he is. Really good. So that's pretty cool, man. That's we got a whole lot of good content coming on today, man. That's really awesome.
Thank you. I appreciate that. Nice work, Ian. Great
Very
job.
good work, Ian. Congratulations.
It's amazing.
Yeah, very concise and very useful. Well done.
Yeah, that was really cool.
Ian.
So do we have any more questions in the chat, guys? Do you have anything you want to ask or talk about? We'll give you a couple seconds to write any questions you might have.
So I wanted to show you something, Sean, while they're doing this, because I don't know that you got to see it.
Sounds good. Thank you, Stefan.
Go ahead and answer questions if you need to right now.
Sure. Evo makes me a proud Dutch boy. You know, Evo, he's speaking English better than me, but it's often way above my head. I'm glad Ian can catch it with his big brain and translate it to me. Mike Don't says, what is the hairpin referring to? Tesla's hairpin circuit. I know we hear about that. Oh,
Okay.
we have to check this out.
Yeah,
This is
Tesla's hairpin circuit. I'm gonna have to build that.
Yeah.
So this is the one I don't know that you did see, Sean. I know you saw the other one, but I'm gonna show you how I connected this thing.
Sure.
I set up my Tesla coil in this fashion for a reason. I'm trying to go from the Tesla coil with the rod down the center to a second Tesla coil in a bipolar manner. Basically, I just want to know, can I go from the hot of the outside Tesla coil on this one with the rod down the center and then go to another Tesla coil and then resonate it based on the primary to the secondary. Now, normally that wouldn't be a problem if that was your primary circuit, just go into this, not a big deal. But since I'm adding this Tesla coil to start it up with this one wire that goes right here, and that's all I'm running over there, and that wire goes right down to the rod that goes down my Tesla coil. So basically just going to turn it on. The goal is, can I get the energy to go hot out of the secondary of this big coil? We are resonating at 429 kilohertz. We have 16 volts. So I got 3 amps going in this thing. So let's check it out. Does it get hot or not? So let's go to the end here. This wire, by the way, simply attached to our secondary right there. Attached to the wire. Now, yeah, that's definitely hot energy. So, since we know it's hot and we don't want to mess with it, I'm going to try to clip this while it's hot. Yeah, don't try this at home. That's really bright now. Okay. Now, does it still work wirelessly? There's the lights on. I'll turn off the lights in a minute and you can see it, but you can see it over there. It's definitely on. Now, this one's here in between this Tesla coil and this Tesla coil. That's fun. Okay, we're still only at 16 volts. So this is our number 2 coil. Usually I connect this to ground when I do this. This one will be hot. It arcs right there. I think I took it out of resonance. But lights up bright. So let's turn off the lights. Raise this up a bit. And we're going to check with the lights off exactly how much field I have. Wow, those lights are really bright. Wow. Okay. We'll just take a look at the lights because I like light bulbs apparently. Man, those are super bright. So this one is on. Let's see if I can get a good picture of it. There we go. We're on a little bit, off, on, off. You can see it right over it. We're definitely resonating from that Tesla coil. That's really cool. This is the first time I set one of these up. So, yeah, we can see it right here at this end. Sorry, the other light's so bright. Definitely lit up and it's out right there. Back on. So we definitely have resonance for this one. We know our regular Tesla coil resonates. So there it is, nice and bright. So this is a really cool experiment. The energy goes from the center of my Tesla coil, where it's just picking up extra energy, through the wire to resonating this Tesla coil, then transferring the energy back to a hot energy. So that's just amazing. It's probably just how air cores work, don't get me wrong. It's probably something simple. You could probably pick it up in a manual somewhere and learn how this works. But to see it in action, well, that's something else. That's something I really enjoy. So we're good in resonance. I'm going to go ahead and do a few more little playing arounds and maybe spark something. Well, that's just what I like to do. So we'll come back over here. Let's see if I can get a real good tight shot on that. Oh, well, yeah, look at that. It turns it more into high voltage. Look at that. So I'm going to end up blowing something up. I know it. Go between the two. And yes, I do like to play with that. Ooh, my hand's getting hot. Ooh. Wow. Definitely some hot energy there. Wow. You can see the difference. Watch when that light lights up even brighter. And this wire, man, it's cooking this little wire. Ooh, my hand. Ooh. Wow. Does it bring back the heat? Oh, God, yeah, it does. Yeah, it burned my fingers. It's probably going to singe those wires after a while. Anyway, we'll turn the lights back on. Take a look at it again. Anyway, that's basically it. So, you there?
I'm sorry, I had it on mute, Nathan. That it's so creative. It's like you're meandering down a maze from cold energy to hot energy to cold energy. And Ian mentioned in the comments how give the cold energy to the people or something about and return the hot energy. Giving back the hot energy.
Well, I was trying to show that you can go in between the two states very easily between the transformers, because that's really what they are. Tesla coil transformer, same thing, just an air core. So I went from cold to hot, and then I could always go back to cold again. Now, in another video, I put the wire down the center of my bipolar Tesla coil, and it lights up the light real bright too. So it'll transfer back into cold energy. So,
yeah.
But the one thing is, I just kind of freaked me out a little bit when I did it, is I used one wire to start up a Tesla coil, not two. There wasn't a ground wire attached to it. I might have got more energy out of it. There's one single wire, and it was just a pulse magnetic field that was going on in that primary in order to get that secondary to resonate.
was the primary Tesla coil data source, was that a ZBS?
Yes.
Yeah, it boggles the mind, Nathan. I'm sorry. The reason is that the ZBS, once you set it to a particular resonant frequency, it's sort of locked in. So the fact that you're able to string along these coils and then they start resonating, yeah, I mean, you stumbled upon something very new, at least from my understanding and research. So that's worth looking into right there.
Well, you see where I'm clipping the wire at on there? There's a reason why you clip it at that certain point. So I've gotten to the point where I can manipulate my primary Tesla coil wherever I want. I can go up, I can go down the frequency in order to find resonance with whatever capacitance I add to it. So it's like playing with a cap bank, but you're moving the wire instead.
So you can either adjust the inductance or the capacitance when you're affecting the frequency, but it doesn't seem like there's enough inductance in the wires that you're connecting to have that much of an effect. And you're not changing the capacitance. That's what's really interesting about this. I mean, unless the capacitance of the other coils is affecting the resonant frequency. To be honest, I don't know. I'd have to watch this a few times, take notes. I can say though that you've opened up a lot of doors for experiments right here.
Yeah, because whether people know it or not, I just gave you one of the fundamental keys to free energy. And I made it easy to find that you're going to get it out of that magnetic field of your Tesla coil, but you don't have to use a Tesla coil for this. You can use geometry coils to get the same thing. The fact that I converted it back to a high voltage energy like an AC flyback is what's amazing about it.
Right. Yep.
So,
Nathan, not to change topic real quick, but Brant had a couple questions for you.
yeah, go for it.
Can you provide a gravity flyer update?
Yeah, I just started running it again. I went through the testing of it. I'm going to run it outside and show the test on it. Something I've previously done, so I'm just going to do it again, and I just put everything back into it. I blew up several high voltage modules on it while doing the test. The energy it puts out is amazing, and it goes very far, and I want to show that. So that's why I was just doing the simple test this last time when I showed it, just to make sure the fields are there, they're present. I want to see how much voltage is in there by the distance of the, wires. And I think I need to double the voltage. So right now I'm at 12 volts on there, and I think I need to double it to 24 volts in order to push the right field that I'm looking for. But yeah, I'm going to show it outside with some big distance. Like you saw the lights outside for the one-wire energy. This time I'm going to put hot energy into it and the cold energy, and I'm going to manipulate the fields in order to push that distance. So yeah, that's basically what's going on it. And then I'll be showing some of those tests and the good ones coming up. So it's going to be interesting. But yeah.
Yeah, thanks for that. Thanks for that, Nathan. So you're going to be in the backyard with the Graviflyer right next to the multiple light water crater you have there, illuminated at 2 a.m. in the morning while you're in your boxers.
Yeah, I wasn't in my boxers. I was in my pants, but I was mooning everybody, so I had to put a sensor over it. That was pretty bad, but no, it's drained now. So there's a little gopher living in it. So hopefully the gopher gets out of the way, because we're going to be running some voltage he won't like.
You're going to light up his life.
Yeah.
That's awesome.
No, it'd be fun because, you'll see the dirt and everything, and it won't be one of those situations where you're wondering what's under it, because there's nothing under it. But it'll be able to push the energy out. You'll be able to see it.
That's awesome. There's some some love in the comments about your Grab a Flyer update. So thank you. Society of High Sciences says it was going to be a full moon that night.
Oh, it was shining all right.
That's clever. Yeah. Somewhere a plumber dropped his wrench. Sorry, that's bad.
That was me.
So Brent also asked about connecting the Tesla coil to a homopolar motor. Now, no jokes about that. All right, it's a real thing. It's I think it was invented by Faraday. And it's basically a copper disc that spins, and it's all current, no voltage. Well, almost all current, almost no voltage. And Brant here is saying, have you thought about connecting to a Tesla coil? So a Tesla coil is high voltage, low current. And it's, oh, by the way, it's AC, but the homopolar is high current, low voltage, DC. What do you think, Nathan?
It's interesting you brought that up. Now, I want to say it's a Testica experiment. And it has to do with a Wilmhurst, what looks like one. Okay. But I think what's missing in there is that single magnet in between each one of those things on the Wilmhurst, right? So, and how do I want to say this? It would like be putting a disc in the center or something like that of magnets or on the outside, and you're getting high current with high voltage and they mix. So, even if it's just static electricity based on the experiment I showed you, I can still convert that over to hot current, and then I can use the MEG in order to pull the magnetic fields together and combine them. So I think there's a way to do this, and that machine is a free energy machine. So based on what the whole thing we're doing here with all the different energies, we may be able to pull something like that off. Now, it's going to require a ton of testing in order to get it right. But
oh yeah, AC/DC, baby.
Yeah, it's going to be something that we'll just rectify it on one end of it, whichever one we come out with. But I can get it right. It all depends on how we build that core, and that's why I'm looking at the air core. And if I can build it in layers and just activate it in different layers, I'm sure I can get it right.
So are you saying that you're going to put together a MEG? Because with your building skills, I think you're the perfect person to build it, to be honest.
I'm going to put together two of them. So they'll be horseshoe shape. So just a little U. And at the bottom, I'm going to connect the magnets in between, right? And then I'm going to wire it up. Now, the goal here is pretty relatively simple. I want to get an extra field out of it. So you always hear Gerald talk about anomalies. Well, that's what I want to do. Hello?
Yeah, sorry, you sort of hung up there. You say again? The last part?
I'm completely frozen right now.
Yeah, we can hear you though.
Okay. Anyway, I want to try to combine the fields in the MEG. So if I could put the high voltage with the high current in there and just put it on different sides, can I combine the two to make something good?
Yeah, I think, Nathan, the two screenshots that you sent me today, one of the MEG and the other one of the free energy device, did you want to reference those or maybe for another time?
I think we're going to do it another time. But yeah,
okay.
I think it's one of those things that I can't even show my camera. I don't know what else failed. But it's one of those things that I really want to go over in detail on how I'm going to do it, because there's going to be a whole lot of questions associated with it.
Oh yeah, a whole lot. Every time I see somebody work on the MEG, it's always almost. They get all the materials together, and then they tell you what it's supposed to do, and then they say it's almost there. And so it would be really good to see somebody like you, an experienced builder in this area, to put your focus on something. Just for me too, I've always wanted to build a meg, but I have a complexity level that I can't exceed. But if somebody like you, who's a good teacher, it would be great to sort of follow you along on that. So Ben, are you still on?
Yes.
You had to think about it for a minute. Oh, it's so great.
A whole bunch of thoughts came to mind to your comment, Ben. Sorry. So Ben, do you have an update on what you're working on? Anything new?
I do have an update on the dual thief setup that I've been running. Some interesting news. So we have been running the dual thief for I think it's the third test now, just to confirm the readings, and it's lasting about 24 to 25 hours on twice as bright as the single thief, the lightning thief, which was about 3.3% brightness. Now, this is interesting because it still shows significant energy gains, but at a 80% efficiency of the single lightning thief. So what I mean by that is it's not as efficient as the single lightning thief, but I have a couple of theories on that. One theory is the second coil that I'm using with the second lightning thief for the setup here is missing an entire wind. So I was short by one entire wind on the coil. I was short on my wire. So it's missing an entire wind for the frame. That might contribute to the efficiency discrepancy there. So I'm not ready to give up hope on the dual thief setup. It could still prove useful. And as it stands, it does seem to be getting at least 24 to 25% more efficiency than the inverter. So if I can bring up the results here real quick.
Yeah, that sounds great.
So let me switch this over here so I can see it. All right, so this is the comparison of the single to the dual. Ignore those two graphs; those were outdated graphs. So the voltage drop rates over time for the dual thief seems to be steeper than the single core thief. The single coil thief. I'm on the wrong thing here, I think. Oh, no, there it is. Okay, so the dual thief only lasted about 15 hours and 30 minutes relative to the same discharge rate as the single coil. So this was the first 15 hours. So actually, this is outdated too. Okay, so I'm just going to tell you what the results were. Here's the graph. This is the graph I'm looking for. Can you see it? No, you can't see it.
No, we can't see anything.
Hold on one second.
So just tell us what happened, Ben.
There we go. Okay. So the single coil lasted 60.5 hours, the single lightning thief. And the inverter, when adjusted for the power factor and everything, lasted around 38 hours. Okay. So the inverter we know is already getting around 90 to 96% efficiency. We measured it at 96. We also have it in the graph here somewhere where we assume the 90% as well. But at any rate, we can see the difference in efficiency here, 0.714 to 0.457 on the coil and 1.8 0.254 watts to 0.614 watts. It's a little bit steeper of a efficiency loss. So that's right off the bat, we know that the system is acting a little bit more efficient regarding the losses coming in and out. Now, this is a better graph where you can see kind of like clearer how much efficiency loss is in the inverter on the right compared to the coil, the lightning thief on the left. Now, the power level, while it's a lot less, the efficiency seems to be a lot more. So if we can boost that power level, which we seem to have done with the dual thief setup, at least twice as much by eyeballing it. Again, I don't have a lumen meter or a detector or whatever to measure the lumens. It's at least twice as bright, in my opinion. So that's pretty significant that we boosted that while maintaining the same efficiency. So relatively, with about 80% of the same efficiency. So that's pretty significant. One thing, oh, here's the setup here. Here's the two lightning thieves that I've been running on the top, each with their own coil, one the Mark I coil and the other one with the Christmas coil that's missing the wind. Okay, and that's the indicator light there. While the margin of errors seem to be wide in these tests, they still fall within the confines of indicating significant energy gains. Now, we still need to confirm these, but Michel Morel had some really interesting updates that I'd like to read for you real quick. That kind of, he's going to confirm them with the oscilloscope, but if he does, they will actually, in fact, confirm the readings that I've been getting with the current, which seem to be very minimal loss or even maintaining the current on the output, which is significant when you're significantly increasing the voltage at the same time. So what he had to say, he said, he was testing, and this is a different circuit, by the way. I'm not really sure which circuit he's running for his coil, but he's running the PoE coil, which is the same as the Christmas coil I have, the same frame. And he said he's putting in 250 milliamps, and the output into a 5-watt LED is 1.3 amps. Okay. And he's measuring 3.5 watt. I think he said he's measuring 3.5 watt input to 8 watt output. I have to confirm that. His sentence is a little jargoned right there. But at any rate, he seems to be maintaining or even increasing the amperage. So that's significant because that seems to be what's happening with the coil readings that I'm getting with the current. I just did some current readings earlier, and I got and it's a little tricky because we're oscillating the current and we're resonating the not just the load and the the coil and the capacitor, but also the battery now as well is in resonance. So it's tricky. So I wanted to measure both the AC and DC current just to see what it would read, and it basically read almost the same thing, which is very interesting. But with the DC current on the output of the battery, we got around 220 milliamps. And with the AC reading with the amp clamp, we got about 200 milliamps. So that's very interesting because on the output, we basically have the same readings, only slightly different with minimal loss. Very minimal loss. And right out of the coil, I think I measured on the Mark I coil, there was no loss. It was 200 going in, 200 coming out. So it's very, very interesting readings there.
Very cool. Yeah, you got a lot of different stuff going on. All right. So you're getting it to light up brighter, and you say you're getting more amps or slightly more amps?
Yes. So while we didn't get the exact same efficiency rate that we got with the single Lightning Thief, we got about 80% of it, which is still about 24% more than the inverter. So, and remember the inverter is already at 96%. So it's pretty interesting. Yeah, the panel lights up way brighter with 2 coils. The one coil though, the Christmas coil, only reads about a quarter of the amperage. Like it's still maintaining the amperage, right? The input versus the output, the readings. But it's like, okay, so the Mark 1 coil will be drawing like 200 milliamps versus the Christmas coil, which only seems to be drawing 50 milliamps. I still think it has something to do with the capacitor and the LED panel that's messing with everything. I think if we eliminate that, we might get a little bit more brightness. So, who knows?
I got a question, Ben.
Hmm.
First of all, nice work, and I'm really liking the metrics. There's a saying, you cannot control what you cannot measure. So I'm really digging the metrics. Have you placed a different kind of load other than the lights? I know you talked about maybe turning a small motor when your sphere was in the glass jar and it had that force moving it to rotate. Is there what's your plans for that?
So that is using a different system to power it. It's using a stereo amp mini board. And that is interesting because I haven't really found a use for that other than wireless induction. So what I mean by that is, it has to be like a closed circuit. You can't really attach a load to it. As soon as you attach a load to it, the electromagnetic field, it dissipates. So the only real way that I see that being useful is if you use the free energy that's coming out of it through the wireless induction method by using a pickup coil. And then you can just basically power lighting. I'm not really sure other than that what you can do with it. Again, I want to get the green machine out to you guys. That's what my plan is for 2025, is to get the Lightning Thief prototype and green machine, which will emulate that test as well.
Sure.
And it will just basically be a plug-in and play system, like you'll be able to monitor the input and output wattage on the LED panel, the RPMs, everything. You'll have a timing system, everything right there in the little box. And all you'll need is your bifilar coil with 2 channels. That's it.
Incredible.
So that's going to be really fun. We have the PCBs printed and they're already on the way. I'm going to go over some ideas on how to case them in the box that I have, and maybe I have to redesign it a little bit, but we will try to get those out to you guys to test. So maybe you guys can figure out, like what these would be most useful for, because again, these are going to go out to you guys so you can kind of like beta test them for the consumers.
Sure.
So, before we roll out with the consumer versions.
So Ben, just an idea. If you used Ian's cap bank, and you probably wouldn't use nanofarads, but you'd probably use a higher thing than he had. But couldn't you adjust the load on it based on that? So if you wanted to pull it through,
Yes,
you put it into the cap bank and then put it hooked to the lights, and then adjust each one of them until you get to the right one.
you could exactly do that. I was thinking the exact same thing when I was watching that switchboard and having him explain what he uses it for. That kind of like put a light bulb in my brain. Yes, absolutely. I don't know if I have time or the resources to build one at the moment, but when I have the time, I will try to build one of those because that's going to be useful. The load has to be perfect. You have to tune the load. You have to pick the load to go with the circuit that you built.
Yeah. Sorry, I was even thinking the ones that I keep taking off of my Tesla coil circuit with the GVS. All those caps, you could just use them and put them together and see how many of it took to get there. So if you have extra ones like that, even if they're not like Ian's real specific, it would help.
That's actually, you know what? And I think that's the missing piece of the tuning puzzle. Because as you see, like Michelle and I have kind of come up with different ways to easily tune your coil. So you can tune it into resonance with the lightning thief and potentiometer. That's what we're going to have for you guys. So you can tune your coils into resonance. And then to tune the coil with the stereo amp board, you have the method where you kind of slowly crank it up from 7.83 hertz, saturated in that frequency, and you kind of just like ramp up the frequency a little bit, 1 hertz at a time, right? And you kind of like catch it, you know, and then you can kind of speed it up real fast. And the closer you get to that resonant frequency, the more efficiency I think you'll get out of that. But that's the way you tune that. But I think you've came up with the way, or Ian, you know, has shown us the way to tune the load. So this is very important, you know, and the battery, the source has to be tuned as well. You have to pick your battery correctly. Like Bedini said, you know, 12 to 20, what do you say? 12 to 24 amp lead acid battery.
Mm-hmm.
Yeah. So, I mean, it all has to be chosen carefully. So it goes together. You know, the capacitor changes the frequency, obviously. So you want to choose the capacitance carefully. You want to choose the load because the load can act as a capacitor. So it
Sorry, did you say 12 to 24 amp?
no volts.
Oh,
Did
sorry.
I say amps?
I heard amps.
If I did, I apologize.
I was gonna say you're gonna blow up a lot of stuff.
Nice.
When I'm on a roll, sometimes I'm on a roll and you can't stop me.
Sorry, it just sounded wrong. I was like,
No.
wow, that's some hot coil.
that would blow you away.
Yeah.
You're gonna be like Electro Boom if you sit on it. Your butt's gonna be burning, man.
Oh boy.
That's bad.
Right. So that sounds great. You make some good points, Ben, how it's a super balanced system, how you need to achieve the right resonant frequency. You
But
mentioned
having the coil though, and having the geometry of the coil makes it so much easier to do that. Because once you have that base component, you can, like I said, you know, with the lightning thief, easily find its resonance, right? And then you're golden. You can work from there. And it's just in retrospect, it's going to be a very easy process to do. And you know, since I see so many of these coils already sold on Etsy and all that, I'm just going to go ahead and have a version of the green machine where it has a small coil in it, you know?
So are you looking to, once you get this with the right outputs that you're hoping for, are you looking to then sell it, or are you going to open source the plans?
So everything is already open sourced. Yeah.
Okay.
The lightning thief is open sourced. You can go on my channel and view Michel Morel's circuit. It's just a modified abut excitation circuit, which is a modified jewel thief circuit. So it's a simplified component. So everything is streamlined for you and your coil. We're going to be selling kits, you know, it's coil kits. So, you know, like you can put them together. But since I've seen so many on Etsy already, I'm just going to go ahead and have versions that already have the small coil built in, you know, because I want this technology out there. You know, I want people to have it and use it. They need it. You know, people have been asking me for it, and, you know, like, I have the means. So
no, that's awesome. I've seen the coils you're making reference to on Etsy, and they're obscenely expensive. Do you think that you might find a market with cutting the cost in half and still making a profit?
Of course. That's the main goal is we want to sell these as close to cost as possible. You know what I mean? Like, the idea is to get the technology out there and not have it be like some elitist technology like we've seen like with the Rasha technology. You know, like, you know, they have implemented these coils, but it's like expensive sessions that only, you know, like really rich people can afford. It's not aimed towards a general, you know, consumer base. Whereas like people need to save a little bit of money. It's not going to replace anything, you know, but it's, you know, imagine a system that you can, you know, jumpstart your car on a 12-volt battery that's dead, right? You know, you have
Yeah.
a dead 12-volt battery in the back of your car, you know, like for emergencies. You have
Yeah.
the system that I have. You hook it up and you jumpstart your car. You know, it's just an emergency system. Something to save you a little bit of money for efficiency purposes and lighting and heating, stuff
Sure.
like that.
Well, I mean, every little bit counts. It just depends on your market. When I look up parts for a microwave oven, and I see that the parts are expensive, and why not just buy a new one? And after doing a little bit more research, the majority of the world can't afford to buy a new microwave. They
Yeah.
So they have to order a part to fix it. And
Mhm.
I feel like there's maybe a market there where people are looking for energy efficient systems because maybe they don't have a lot of money into their home, but they want to light it. They want light, and yet they're in the third world. And so, have you thought anything about that?
Yeah. Yeah. I mean, if you look at what I'm doing right now, I'm lighting, you know, my living room with the lightning thief, you know, the dual thief setup that I have.
Hmm.
It's, you know, it's fairly bright, you know, it makes a nice light at night. I don't have to turn on any of my lights now. So, you know, I'm saving cost on that end. It's not a lot, it's very marginal. But right now we're aimed at, you know, maximizing that efficiency of the system. That's why I want to get it into your guys' hands so we can kind of tune it, maybe get more
Yeah.
efficiency out of it. But also, yeah, you're right, we want to get these devices into the hands of people in third world countries for sure, because
Yeah.
at the end of the day, you know, most of the world, we live in this bubble in America, but most of the world is in poverty. Most of the
Oh, of
world is,
course.
you know, and they're struggling to get, you know, like save on energy, or, you know, they got um whatever they can do. So I think whatever we can do with these systems to make them inexpensive and
Yeah.
affordable
Right.
is within our responsibility, if that makes any
Yeah.
sense.
I like that point. When I first moved to, I'm from Southern California, and when I moved to the Chicago area, I had my first winter, and I thought to myself, well, what if the natural gas is uh, is cut off, and for some reason I don't have the ability to warm my home? That made me nervous. So I
Right.
had installed a wood stove, and then to test it for one whole year, I only allowed heat from the wood stove to heat the whole house. Now I had a young wife and 4 kids at the time. I was a drill sergeant in the Navy, and I was able to go 3 straight years without turning on the gas. Is there something akin to you using your invention to say, I haven't done this for uh, for the entire year because of this device?
So right now the efficiency for the lightning thief seems to be around like 155%. It's not able to like close the loop, so to speak, and get like you know, infinitesimal amount of extra energy output compared to the input.
Hmm.
That happens around like 200 or so, you know, accounting for, you know, various losses in the system. You might have to have more than 200%, but around 200% efficiency is when you can kind of close that loop and kind of see that kind of significant, where, yeah, you're replacing systems completely. You know, that's kind of like the end goal here. Honestly, I do want to get there, but we're not there
Yeah,
yet. And I don't want to like, I don't want to make claims of over unity. This isn't an over unity system. It's showing
sure.
significant energy gains, and it's
Yeah,
showing 155% efficiency, but that's not verified, right? So you know, you have to take that with a
yeah,
grain of salt, and you have to just go with the flow of my tests and be patient, and we have to see what this thing is capable of before we can make any claims like that.
sure, sure.
um Yeah, but at this moment, it does seem like it's going to make a good efficiency, like backup generator, like, or backup system, like, so you have a 12-volt battery charge for backup emergency purposes. You
Yeah.
attach it to, say, see the green machine down at the bottom that has a built-in small coil, right? And you have various attachments that you can attach to it for, say, induction heating. So you want to heat your little small 1-bedroom apartment living room like me, and the power goes out with the 12-volt battery. You can heat that, it'll last, 1, maybe 2 nights, maybe 3 nights, who knows, right?
Wow.
And then I'm assuming it's going to last at least 2 nights like that with the heater.
That's great.
Yeah, that would be amazing.
Amazing.
And then we take the attachment off and we put a little George Foreman type grill attachment, and you have your little cooking stove,
Nice. Yeah.
Cooking with the coil or whatever you call it.
Nice.
Cooking with a coil, CCC? No, CWC.
Yeah, so yeah, I mean, this is what I was thinking of when I was like, oh crap, the winter's coming up. I don't have a lot of, like savings or money or whatever to get a, a proper generator for my apartment. Like a big APU. My APU is busted. It doesn't hold a charge anymore. So let me try to, get this in order. And I do have the lighting down. The lighting is going to be, no problem. As long as I keep that battery charged, I got lighting for 3 days. You know what I mean? So
yeah.
The heating I know how to do. It's not hard, but I haven't tested it yet.
The 150+% efficiency is earth shattering. I mean,
it's
can't
pretty hard to wrap your head around.
Yeah.
But that's just what the data shows at this moment, and Michel is showing some really amazing data regarding he says he's close. He's not there yet, but he's close to over unity, and he just needs to verify some things. And I think he's there. I think he's right there.
That's awesome. You guys are a good pair.
Yeah.
Thanks for sharing.
Yeah, no problem. I appreciate it. Yeah, it's very, very exciting times.
It is. Nathan's OWE. And I tried to create an acronym for my Tesla coils. The MTC, the multi-layered Tesla coil. I think that's not in the vernacular yet regarding Tesla coils. And so, Ben, now it's on you to put out your acronym for your because see, one wire energy's been done with Tesla 100 years ago. Tesla coils that I work with, though, it's a different slant on it. It's again 100-year-old technology. So you're just putting together a design that's unique, and we're going to test that. Have you thought about what you want to call it?
I haven't given it much thought, but I'll get back to you on that.
Sure. Sorry, I don't mean to put you on the spot. I know it's a big question. It reminds me of reading Jarvis's paper on Electrets, where he wants to call it bacon shake.
Oh, nice.
Bacon shake method of building Electrets. And it's catchy.
Well, I did come up with the name for the shop that we're going to open. It's called Coil Kits with a K. So 2 Ks, Coil Kits Lab Shop. So I don't know.
Nice.
Maybe we can turn that into an acronym of some sort.
I like Coil Kits with a K. That's very cool.
Yeah. With a KZ. Yeah, KZ instead of an S at the end.
Just make sure there's no K anymore in that acronym.
No third K.
Do not add a third one. Just don't do it.
He's like, don't do it.
I can guarantee it will be not good.
I would change the first letter to a C myself.
That might be a better idea, Nathan.
Yeah. Sean, all I kept thinking about with your coil was the big blue balls we saw, like the blue balls of the mini. I don't know, man. That's bad.
Oh my goodness. Oh boy. I don't know who said that, but they need a timeout.
We'll put the dunce cap on him, put him in the corner.
Gonna get my mouth washed out with soap.
I forget who said it too, but I won't point fingers.
Oh, man.
In the chat, special K coils.
Oh, nice.
Because Ben, you're special. That was
Thank
bad.
you. I appreciate it.
Oh, wow.
All right. Well, a lot of good stuff coming tonight. I feel super awesome, Nathan, you letting me share, and I really appreciate you all in the chat. And Ben, I appreciate you as a sane shoulder to cry on, a sounding board. But it's that same bat time at this bat channel.
Absolutely.
Well, time to hit that old dusty trail, ladies and gentlemen.
Yeah, we're so let me just get this out. We're gonna be Friday, Ben and I do not think Mike is gonna be back this week, so we're gonna be doing his show on Friday. So League of Extraordinary Inventors, and then Joe's back, so we do Saturdays with Joe, which is gonna be awesome. So yeah, that's what I got going on. Ben, how about you?
Honestly, I don't have a lot of going on right now, but I do have those PCBs coming. So what I'm going to be doing in the next couple months is trying to get a couple of those prototypes together for the team.
Okay.
That's really the only thing I have going on right now until I figure out my next move. I honestly don't know what next set of tests I'm going to do. So,
Gotcha. Sean, are you working on those Electrets this week?
Yeah, that's going to be my focus. So now that I've also heard some good ideas in the chat, SOHS, Society of High, I can't say the whole name, but he came up with some cool ideas that I screenshotted and in the chat. So something about doping and clay and very cool stuff.
Right on.
So yeah, I'm going to keep that as a primary experiment, and then try to clear my backlog. I got to get that pyramid, arcing and sparking, and play around with these golden ratio coils.
Right on. That sounds good.
nice.
Well, I'll be doing a couple gravity flyer experiments here in the next couple days, and hopefully work this thing out to where it's good. I'm waiting for a delivery in the morning. I blew another ZVS board today.
No,
I know
I'm sorry.
myself and a lot of people are excited about your new Graviflyer video updates.
Well, I keep blowing things up because I keep pushing the limit. So I sometimes, man, I wish these EVSs would go up to like 100 volts, man, because sometimes you need the power. Sometimes you're just messing around, and if you leave it on there too long, things explode, start to smoke, and little fires go on. So yeah, I'm gonna have to get better at that. But yeah, wait for a delivery in the morning to get that going. So. All right, guys, it's been fun. Thank you guys in the chat, man. I had a great time in the chat today. And Sean, thank you for presenting today. It was totally awesome. I also want to thank Jarvis for sharing as well. I wish he was here in person. We'll have to see him again next week, maybe.
Yes.
And Ben, thank you for all the updates and everything, guys.
Oh, you're welcome. No problem.
And thank you, our fearless leader, Nathan.
Oh,
Yes,
thank you.
Nathan.
Right on,
right.
guys. It's been fun. Have a great night.
Have
All
a good
right.
night,
Talk
everybody.
soon. Bye.